good afternoon or good night to everybody. So this is really exciting, and it's a real pleasure to have this thesis presentation by Carlos Correa on cosmic voids as cosmological laboratories. Just a few words. We will have first Carlos' presentation of his thesis, and then we'll have questions from the committee. No from the public, just from the committee. And then we'll have room for public comments and questions. And then, unless the committee has already decided, we go to a private meeting by the committee, and then we will be back for the final assessment and remarks from the committee. Okay, so we start with Carlos, and then questions from the committee, and then public, and then private meeting by the committee, and the final assessment. Carlos,
okay.
Go ahead.
Well, thank you very much. First of all, I want to thank you for being here in this day so important for me. I'm going to present the main results of my PhD research during all these years. I have focused on the study of cosmic voids from the point of view of cosmology. So this is the content of my exposition. It is divided in 3 main blocks. Each one is a different project that we developed, but they are all connected. Before I start, I want to thank here my collaborators, Dante, also my supervisor, Nelson, Ariel, Andres, and Raul. Without their help and very valuable contribution, this day would not have been possible, so thank you very much. So let's start with the introduction and goals. Over the past decades, we have entered in a high-precision cosmological era. The latest observations show that the universe is not only expanding, it is also accelerating. The standard model of cosmology postulates a flat lambda cold dark matter universe, in which this cosmic acceleration is explained by a new component called dark energy. From a theoretical point of view, this dark energy component is consistent with the cosmological constant in the Einstein field equations. But it could also be a hint that we need to review the laws of gravity. I mean, to review the theory of general relativity. Even worse, this component is the dominant one. It contributes to almost 70% to the total energy budget of the universe. So this dark energy problem is one of the major challenges of modern cosmology. Now, what are cosmic voids? The standard model, and in general every cosmological model, rely on a fundamental assumption, the cosmological principle, which states that globally the universe is homogeneous and isotropic. But of course, this must be understood in a statistical sense, as we see here in this figure. This figure shows the spatial distribution of the galaxies taken from the Sloan, one of the most important spectroscopic surveys built today. From the figure, it is clear that the galaxies do not distribute uniformly. Instead, they group together by the action of gravity. As we can see here, galaxies trace the large-scale structure, forming different structures like groups of galaxies, clusters, filaments, and walls. And complementarily in this process, they also leave the underdense regions of the universe, making them even emptier. These are the so-called cosmic voids. In this figure, cosmic voids are represented by the darkest zones. The statistical properties of voids depend on 2 conditioning factors. One, the tracers used to identify them, namely galaxies, dark matter halos, dark matter particles, in simulations, for example. And the other one is the void finder used to identify them. There are different classes of void finders based on different techniques. Here I show you the 2 of the most important, the watershed algorithm and the spherical algorithm. However, despite their differences, there is a consensus on basic properties of voids. For example, they are huge regions with sizes of tens of megaparsecs of diameters. And also their density is between 10 and 20% of the mean density of the universe. Now, which is the connection between cosmic voids and the dark energy problem? Well, voids are the largest observable structures, so they encode key information about the geometry and expansion history of the universe. Hence, voids emerge as natural candidates to test dark energy. Moreover, voids also contribute to two special advantages over traditional clustering studies. On the one hand, the evolution of voids can be followed by a linear approach very well. And on the other hand, voids are ideal for testing modified gravity theories because these theories predict that potential deviations with respect to the prediction of general relativity must be most pronounced in these unscreened low-density environments. The potential of voids is also enhanced in view of the new generation of galaxy spectroscopic surveys, which will prove our universe covering a volume and a redshift range without precedents. Up to date, the three most important experiments for dark energy are the Hubble diagram using distant supernovae, the study of CMB anisotropies, and the Alko-Paczynski tests using the characteristic scale of the baryonic acoustic oscillation. Here in this plot, you can see the cosmological constraints from these three experiments here for these two fundamental cosmological parameters, omega matter, which quantifies the matter content of the universe, and omega lambda here, which quantifies the dark energy content of the universe. The most important aspect of this plot is that even the individual experiments could manifest large confidence regions. The joint analysis of them allows to place tight constraints on the cosmological parameters. So, which is the goal we pursue with voids here? To complement with such an analysis of this kind. So, there are two main statistics in void studies, the void size function and the void galaxy correlation function. Mathematically, the void size function quantifies the number density of voids as a function of their size. And physically, it characterizes the abundance of voids in the universe. It is analogous to the mass function for dark matter halos, so it can be modeled in a similar way using the excursion set theory combined with spherical evolution. In the case of voids, the expansion model. There are two main approaches, theoretical approaches here, the Shed and Van den Weyer model and the Jennings model. Before I explain the other cosmological statistic, the correlation function, let me explain you what are the distortions in the observed spatial distribution of the galaxies. Here, at the left, you can see the matter distribution in a simulation. And here at the center, you can see how this distribution is actually observed. We are assuming a hypothetical observer located here at the center. There are clear and evident radial patterns here. These are the so-called redshift space distortions, a dynamical effect caused by the peculiar velocities of the galaxies induced by the local gravitational field. More specifically, we estimate distances to the galaxies from the measured redshifts from spectral lines. And this redshift has two contributions, one from the global Hubble expansion and the other one from these peculiar velocities. So the distances we estimate are biased by this additional Doppler contribution from the peculiar velocities. But this is not the whole picture. Actually, the 3D map of the universe is characterized by three measurable quantities that characterize the position of galaxies. Two angles on the plane of the sky and the mentioned redshift, which is an indicator of the radial distance. So we need to transform these observables into a comoving distance scale in physical units, in this case, megaparsecs. And this transformation involves cosmological equations, for example, expression for the comoving distance or the Hubble rate, which in turn depends on the cosmological parameters. Then we need to assume some values for these parameters in order to perform this transformation. And if we make a wrong selection, then we are going to obtain, again, biased estimation of the distance, and again, distortions in the distribution of the galaxies. This is the Alko-Paczynski effect. And in observations, both effects manifest coupled. Now, let's return to the other void statistic, the void galaxy correlation function. Mathematically, it quantifies the excess probability of finding void galaxy pairs at a certain distance with respect to a homogeneous distribution. But physically, it characterizes the density field around voids. In real space, the correlation function is simply a one-dimensional profile that depends only on the void-centric distance. This is because of the spherical symmetry imposed by the cosmological principle. But in Redshift space, where observations are made, this spherical symmetry breaks into a cylindrical symmetry due to the presence of Redshift space distortions. So it is better to study the correlation function as a two-dimensional map with one axis in the plane of the sky and the other axis perpendicular to it along the line of sight. In the literature, there are many models for the Redshift space distortions in the correlation function. Here, I mentioned two of the most important, the linear model and the Gaussian streaming model. Okay, before I start explaining my first PhD project, let me introduce the data set that we used throughout the work. So the main data set was provided by the Millennium Extra Large simulation. All our tests and models were calibrated and evaluated using this simulation. It is a huge simulation with a great resolution and volume, which makes it ideal for feasibility analysis for cosmological tests to be applied in modern surveys. The simulation was built with the gadget code using a standard flat cosmology with these parameters, but I want that you only take in mind this value, the omega matter value, 0.25. And also we tested for 3 different snapshots corresponding to 3 different redshifts. As matter traces, we used dark matter halos identified in the simulation using a friend-of-friend algorithm. Now we need a method to identify voids. For that, we used the spherical void finder developed by Padilla et al. And optimized by Ruiz et al. And this is a central aspect of our work. The process of void identification consists on 5 main steps. But the most important thing to highlight is the kind of output. The method returns non-overlapping spherical voids with a well-defined center and a well-defined radius from which an isotropic flux is observed. This characteristic is very important because this means that the voids we obtain are genuine voids with a well-characterized structure and dynamics. To visualize how the method works, here I show you a slice of the simulation with the distribution of the halos and the voids identified in it. You can see here how voids are distributed in the underdense parts, in the underdense regions. Okay, now I am in conditions to explain my first PhD project. It is a new cosmological test based on the correlation function. This work was published in an international journal. Here I leave you the link if you are interested in more details. These are the main characteristics and novel aspects of our method. As a basis, we took the Gaussian streaming model to model Redshift space distortions in the void galaxy correlation function. The first novel aspect of our method is that it is fiducial-free, because we treat correlations directly in terms of 2 measurable quantities between void galaxy pairs: the angle they make on the plane of the sky and their redshift difference, an indicator of their separation and along the line of sight. These 2 quantities here. So in this way, it is not necessary to assume a fiducial cosmology, and then the Alko-Paczynski effect is taken into account in a natural way. The second aspect is related to a third type of systematics besides the Redshift space distortions and the Alko-Paczynski effect, that is that can generate biased cosmological constraint if it is not taken into account properly. We call it the scale mixing effect, and is due to the binning scheme used in the measurement process and the distribution of voids throughout the slice of the catalog. The third novel aspect is related with the previous one. As we take into account this effect, this allowed us to work with fully projected correlation functions. Specifically, we worked with two perpendicular projections with respect to the line of sight. In this way, we can easily break the contributions from the geometrical and dynamical distortions. And finally, the fourth novel aspect are the covariance matrices associated to the method, which have a significantly reduced dimension, which facilitates a lot the likelihood analysis. So here I'm going to explain how to measure these projected correlations. Here you can see a classical correlation map, a classical two-dimensional correlation map in redshift space. So first, we project the correlation function towards the angular axis in a given redshift range, obtaining in this way what we call the plane of the sky correlation function, a function that depends only on the angular coordinate. And in a similar way, we project the correlation function towards the redshift axis in a given angular range, obtaining in this way what we call the line of sight correlation function, which is a function that depends only on the redshift coordinate. So to measure the projected correlation functions, we used data from the Millennium simulation. Specifically, we selected void samples from the radius distribution, imposing a cut between 20 and 25 megaparsecs. And with these samples, we measured the corresponding projected correlation, which I show you here. At the left, you can see the plane of the sky projection. At the right, the line of sight projection for three different projection ranges, 20, 40, and 60 megaparsecs here. Here, you can see the angular axis, the redshift axis. And the two most important aspects from these figures are the following. First, we note that as the projection range increases, then the correlation flattens. This is because the wider the projection range is, then more scales are mixed in the observations. And the other one is that the line of sight projection is more affected by redshift space distortions. So now that we have our measurements, we need a model to describe them. We developed a physical model that consists on 4 stages. In the first stage, we model the scale mixing effect. And to do that, we need to we start from a bin, a given bin, and from an estimator of the correlation function here. And we need to compute here the expected number of void tracer pairs inside the bins with respect to the expected number in a homogeneous distribution. These are very huge and horrible formulas, but the only important thing here are the kind of variables used to express these quantities. They are all observable quantities, angles and redshifts. And the other thing, the meaning of the integrals. They are volume integrals that take into account the geometry and volume of the bins. So the next step, we need a mapping between our observable quantities and the comoving distance scale. In this way, modeling the Alko-Paczynski effect. Next, we need a model for the correlation function that takes into account the redshift space distortions. And for this, we took the Gaussian streaming model, as I mentioned before. And finally, the last two ingredients are a model for the density profile and a model for the velocity profile. For the first one, for the density profile, we developed an own parametric model that is basically a double power law with 4 parameters, 3 of them free. They are an amplitude, a slope that characterizes the behavior near the void walls, an other slope, alpha, that is a free parameter that describes the behavior in the more remote areas, and finally, a pivot scale, which is basically where the slope changes here. And for the velocity profile, we derived an analytical expression based on the linear perturbation theory. Here we can see the dependence with one important cosmological parameter, here beta, that quantifies the growth rate of structures in the universe. So in summary, these are the parameters of the model. We can divide it in two sets: the cosmological set, where we have omega matter and beta, and the nuisance set, where we have the velocity dispersion needed in the Gaussian streaming model, and the three parameters of the density profile. Okay, so now that we have our measurements and our model, it is time for the cosmological constraints here. For that, we make a likelihood exploration of the parameter space using a Markov chain Monte Carlo technique. And here I show you the results, the likelihood marginalizations for the two parameters of interest, the cosmological ones here. Sorry. For each snapshot and for each projection range here. The dashed horizontal lines are the target values inherent to the simulation that we wanted to recover. So from the analysis of the constraint, we can make two important conclusions here. First, that the test is robust with a wide variety of redshift and projection ranges. This is a very good aspect of our method. And second, that we obtain better confidence regions at higher redshift. So the model performs better at higher redshift. This is because the model is more sensitive to the Alko-Paczynski effect here. Okay, now I move on to the second PhD, to my second PhD project. It is closely related to the previous one. It was also published. I leave you here the link if you are interested in more details. Okay, I start with the problematic we wanted to solve. Well, once we had our test well calibrated, then we tried to apply it to real data, to observational data, but we found that the test fails with observational data. Specifically, the model cannot fit correctly the measurements, and we obtain biased cosmological constraints. However, discussing with other people who work also with voids, we realized that we were not the only ones. All of us were facing similar problems. So what is happening here if we have our test well calibrated? Well, the answer is in a fundamental characteristic of the void samples used to calibrate the test. Those voids were identified in real space and using the Millennium True cosmology because we wanted to obtain genuine voids to calibrate the test. But of course, this is impossible with observations. We must work in redshift space and assuming an arbitrary fiducial cosmology. So in this sense, it is expected that the redshift space distortions and the Alko-Paczynski effect to have an impact on the void identification process itself, affecting void properties, and in this way generating additional distortion patterns in the measurement. One possible solution is to use a reconstruction technique. That is an algorithm to recover the real space position of the galaxies based on the Seldovich approximation. Nevertheless, this technique has some disadvantages. For example, it is computationally expensive because it is an iterative process. You need to perform reconstruction and the void finding step many, many times because this is a cosmological procedure. It also loses in some way the possible cosmological and dynamical information contained in this redshift space systematics. And it can be quite redundant because you remove the redshift space distortions to put again them later in the modeling. Although it has shown robustness in constraining very well the cosmological parameters. But here we propose an alternative approach. We propose to find a physical connection between the identification of voids in real space and the identification in Redshift space using our spherical void finder. This is not trivial to do, because unlike the case of galaxies, which can be considered particles that are conserved under the Redshift space mapping and only their position changes, the case of voids is very different. This is mainly because voids are extensive regions of space. So some voids could be destroyed in this mapping, whereas other artificial voids could be created. So it is not easy to know if both void populations are really the same. For instance, they have very different statistical properties, such as their number, volume, or spatial distribution. Nevertheless, as a first step to find this connection, we started with a simple visual inspection of this figure. As you can see, both real and Redshift space voids seem to expand approximately the same regions of space. So in order to deepen this idea, we cross-correlated both void populations. Specifically, for each Redshift space void, we assigned the nearest neighbor in real space with the condition that it must lie inside one void radius. We call this pair of voids a pair of bijective voids because this mapping represents a one-to-one relationship between real space and Redshift space voids here. So the next question that arises is, which are the characteristics of this bijective subsample? Who are these bijective voids? So to answer this, we measured the corresponding void size functions. Here you can see the radius distribution for real space in blue and the radius distribution for Redshift space in red. In turn, the solid lines corresponds to all voids, whereas the dashed lines to the bijective subsample. And here we can see a very interesting characteristic. The dashed and solid lines tend to be the same as the radius increases. This is very important because this means that for those voids above the shot noise level, it is valid to assume the number conservation. So voids are practically conserved under this Redshift space mapping. This has a very profound implication because as voids are, these relevant voids are conserved after this mapping, any difference in the statistical properties between both populations of voids must then be explained by some physical mechanism that transforms real space voids into the Redshift space ones. Here in this figure, it is easy to see the two effects that are involved. First, a systematic expansion, and then a systematic shifting of the centers along the line of sight. So how can we describe physically these effects? Well, let's start with the systematic expansion. This effect is a byproduct of the Redshift space distortions induced by the dynamics of tracers surrounding the voids. For this reason, we also refer to this effect with the acronym TRSD, T for tracer dynamics. Starting from dynamical considerations, specifically from the velocity profile in voids, we found a linear relation between the radius in Redshift space and the radius in real space. This constant of proportionality can be expressed analytically and depends on one of our cosmological parameters, beta here. And we found that this linear relation works very well, as you can see here in this figure, where you can see the two-dimensional distribution of voids according to the void radius. Okay, but this is not the whole story. There is more. The volume of voids is also affected by the Alco-Paczynski effect. Reasoning in a similar way, this time starting from cosmological considerations, we found a linear relation between the fiducial radius and the real space radius. Again, this constant of proportionality can be expressed analytically and depends, again, on the cosmological parameters, but this time on the background cosmological parameters, specifically omega matter. But here there is a very interesting difference between the RSD factor and the AP factor. Here, the AP factor can be greater than 1 or less than 1. So the net effect is not necessarily an expansion. It could also be a contraction. It all depends on the cosmological parameters assumed in the fiducial cosmology. In observations, we know that both effects are coupled, so the final relation between the radius in Reggie space and the radius in real space, we must take into account both factors here. Next, the remaining effect, the obscenting effect. How can we describe physically this? This effect can be simply understood if we realize that voids can be considered as whole regions that move with the net velocity. So in this sense, this effect is a byproduct of the Reggie space distortion, of a new kind of Reggie space distortions induced by void dynamics. For this reason, we also refer to this effect with the acronym VRSD, V for void dynamics. So how can we describe it from a theoretical point of view? So it is only necessary to write down a similar equation for the Reggie space distortion shifting of tracers, but for the case of voids. Here, the important thing is the contribution of the line of sight component of the net void velocity. And we found that this linear relation works very well, as we can see here in this figure, where I show you the two-dimensional distribution of voids according to their velocity and displacement. Okay, so if you didn't understand anything, don't worry. I think this figure can help to understand what are these effects. Now I'm going to move on to the last project here. Okay, so in the last part of my exposition, I'm going to explain how this effect impact on the measurements of the cosmological statistics, the void size function and the correlation function, how these effects imprint additional distortion patterns. I'm going to start discussing the void size function. So we started again from scratch, identifying again voids, new voids, but this time correctly, working in Reggie space and using an arbitrary fiducial cosmology. And with the resultant voids, then we measured the corresponding void size functions. Specifically, we used two fiducial cosmology, one with a value of omega matter lower than the true value of the simulation, obtaining this green curve, and the other one, the other fiducial cosmology with an omega matter higher than the true value, here, the purple curve. So these two curves mimic two possible observational measurements. Which is the goal here, is to correct these observations in order to recover the true underlying real space void size function. I mean, this blue curve you see here. To do that, then we must consider the three Reggie space effects that affect void properties. The Alko-Paczynski and expansion effects that affect the volume of voids, and the obscentric effect that affect the spatial distribution of voids. But here, the measuring the void size function involves only discriminating between void radius. So the obscentric effect is not present here. Therefore, the correction can be accomplished simply with this formula that relates the real space radius and the Reggie space radius with our RSD and AP factors here. Remember that these factors depend on the cosmological parameters. So we arrive here at a very important conclusion. This correction must be incorporated in the modeling of the void size function with the excursion set theory in order to obtain unbiased cosmological constraints. In this case that we are using a simulation, we know the values of these factors, so we can test how this correction works. And we obtain the following. So the correction works very well in all scales of interest. And finally, I'm going to explain the impact of this effect on the other cosmological statistic. the correlation function. This is a bit more complex to explain, but again, we have to start from scratch, selecting again new void samples, this time in Redshift space. So we performed in a similar way. We make a similar cut here from the radius distribution with voids with sizes between 20 and 25 megaparsecs. Again, I remark this in Redshift space. And with this sample, we measured the corresponding projected correlation functions. I'm going to show you only the line of sight projection because this is the most important. So in this sense, we obtain the red curve here. So this red curve mimics a possible observational measurement. So what we want to do now is to describe properly this observational measurement. So again, as in the case of the void size function, we must take into account the three Redshift space effects that affect void properties. But nevertheless, don't forget the effects that affect tracer properties that we considered in the first part. You can see here that the Alko-Paczynski and the expansion effects appear twice. Here, they affect the spatial distribution of tracers, and here, the volume of voids. In addition, we have the scale mixing effect due to the projection range, and now the off-centering effect is going to play a major role here. So our model, as I explained in the first part, in its original form, only takes into account the tracer properties. If we naively apply our model here, considering only these effects, then we obtain the dashed black curve here. So compare this curve with the observational one, the red one. The differences are huge. You can see a similar plot here. The differences are huge. So this explains why our test failed with observational data. We need to take into account these effects too. So if we do that, if we now take into account the volume correction and the off-centering effect correction, then we obtain the blue dashed curve here. Now, the deviations have reduced enormously, although there is still a residual deviation here that cannot be explained with these effects. So there is more. And we found the source of this. It is due to the ellipticity of voids. It's a new kind of, a new type, an additional systematic besides all of them. So how can we know this? To understand this, we have to return to the selection of void samples. Here, we defined this band. But we know that voids are bijective. So we studied how these voids were distributed in real space, and we obtained this interesting result. Although the majority of voids fall inside this band predicted by the volume correction, there are two tails here that contribute significantly to the distortion patterns in the correlation measurements. So how we know that these tails, the ellipticity effect is related to these tails? Well, we measured the two-dimensional density and velocity maps, but in real space here, for each of these three regions. As you can see here, this is the density map and the velocity map corresponding to this band here. You can see isotropic contours as expected. But here for the tails, you can see an isotropic patterns here, which is, we were not expecting this because, as I remarked before, we are working in real space. So these anisotropic patterns in real space arise from the intrinsic ellipticity of voids that are the responsible for the remaining distortion patterns. Okay, before I enter to the main conclusions, I want to show you some preliminary results from observational data, specifically from the Baryon Oscillation Spectroscopic Survey data release 12. Here, you can see the projected correlation functions from this data for two samples here. Here you have the plane of the sky projection, the line of sight projection. And here I have written the main effects that affect tracer properties and void properties. Remember that our model in its original form, as I explained in the first part, only takes into account the systematics that affect tracer properties. So now we optimized our model incorporating the volume correction. The modeling for the off-centering and ellipticity effects deserve a more exhaustive and deeper study, so we leave it for a future investigation. And then we wanted to see how our model behaves with this simple optimization. And we obtained the solid gray curves here. Note that our model describes correctly the plane of the sky projection. This is because this projection is less sensitive to the distortions. But our model is still failing in describing the line of sight projection here. Note, for instance, this bump. So this bump is due to these additional distortion patterns, due to the off-centering effect and ellipticity effect. These, again, are two new kinds of distortions not previously taken into account in the literature. And with this result, I want to stress the fact of the importance of modeling all types of systematics here in order to obtain unbiased cosmological constraints. Okay, so to finish my exposition, I go to the conclusions. I start with the general conclusions. The dark energy problem is one of the major challenges of modern cosmology, but not only for cosmology, also for the entire realm of physics, because dark energy is a fundamental mystery of nature. And in this sense, voids are promising cosmological proofs. They have some advantages using tests with voids. For example, they hold key information about the geometry and expansion history of the universe. Their evolution can be followed linearly, and also they are ideal for testing modified gravity theories. And this potential of voids is enhanced in view of the modern galaxy surveys, which will prove our universe covering a volume and a redshift range without precedent. So in the first part of my talk, I presented a new cosmological test that is based on the void galaxy correlation function. And our method contributes with 4 novel aspects. First, it is fiducial free. Second, we take into account a third type of systematics besides the Alko-Paczynski and redshift space distortions, that is the scale mixing due to the binning scheme. Then the third aspect is the way we measure correlations. We use 2 perpendicular projections of the correlation function with respect to the line of sight. And in this way, it is easy to break the contributions of the dynamical and geometrical distortions. And finally, the covariance matrices associated to the method, which have a significantly reduced dimension, so this facilitates a lot the likelihood analysis. Then, in the second part, I showed how the Alko-Paczynski and redshift space distortions also have a very important impact on the void identification process itself, modifying statistical properties of voids, such as their volume and their spatial distribution. The fundamental result was to realize that voids above the shot noise level are practically conserved after the redshift space mapping. So we have 3 effects that transform real space into redshift space voids. The expansion effect, that is a dynamical effect, the Alko-Paczynski change of volume, a geometrical effect, and again, a new type of distortion patterns, due to the off-centering effect, that is also a dynamical effect. And finally, in the last part, I showed how these effects imprint additional distortion patterns in the cosmological statistics, the void size function and the void galaxy correlation function. As a final reflection, I want to stress the fact here, the importance of modeling all these systematic effects in order to obtain unbiased cosmological constraints. For example, for instance, the off-centering and the ellipticity effects that we discovered are responsible of two new kinds of distortions not previously taken into account in the literature. And this is not only important for cosmology. This has also profound implications on large-scale studies per se, because these effects encode valuable information about the dynamics and structure of the universe in the largest scales. So thank you very much for your attention. That is all.